Okay, it's 11:20 second. I'm very happy to have Daniel Stern here from, I think, Cornell, right? And he will talk about new minimal surfaces in S3 and B3 via eigenvalue optimization. Let's welcome him.
So first of all, thanks a lot to the organizers for the invitation. As I was just saying, this is not just my first time here at BIMSA, but actually my first time in Asia at all. I've been really enjoying my time here and at this conference. Right, the only downside of this conference is there are too many interesting talks to attend them all. I see a lot of the experts are at Tristan's, it looks like. That's all right. Okay, maybe I'll skip out at the end and go check out the end of his talk too. All right, but what I want to talk about today fits into a couple of the talks we've already seen. So in particular, if you've seen Xin Zhou's talk about how in recent years we're getting a much better understanding of the space of minimal surfaces in Riemannian manifolds or minimal hypersurfaces more generally, even so in some very simple classical settings, our knowledge is very far from complete. And what I'm talking about here is sort of a new machinery for producing lots of minimal surfaces in some classical settings, based on techniques closely related to Antoine Henrot's talk yesterday, where he's studying sort of classical shape optimization problems for Laplace eigenvalues, or in this case also eigenvalues of some other natural pseudo-differential operators. Okay, so I'll start out with the minimal surface motivation. So I assume people, if they're attending, are probably familiar, but recall that the submanifold inside a Riemannian manifold is minimal if it's a critical point for the area functional of the appropriate dimension, and at the PDE level, right, this is telling us that the mean curvature is 0. And you probably know that minimal submanifolds are important in a variety of contexts, right, as generalizations of geodesics. And they show up, of course, in mathematical physics, also just in our physical world, and in applications throughout geometry and topology, especially since the work of Shane and Yao in the 80s. All right. And if you care about minimal submanifolds in any setting, which I hope you do, then you're interested often in what happens to families of minimal submanifolds, maybe as they degenerate, and you want to study this and their singular behavior by blowing up and magnifying. And doing this inevitably leads to studying minimal surfaces in the two most classical settings. So first of all, studying entire minimal submanifolds in Rn, because when you blow up your manifold here locally, the minimality of your object is preserved and you end up in Euclidean space. And in fact, if you're blowing up at scales small enough where the area density looks the same at those scales, then the monotonicity formula tells you that you end up with minimal cones in some Euclidean space, which are just cones over closed manifold sphere. Okay? And it's this setting of closed minimal submanifolds in the sphere that we're going to start with today. All right, and even though these have been studied for centuries, especially in the case of Euclidean space, where these go back to the 1760s or 80s or something, even in the sort of simplest non-trivial cases, of course, geodesics in these spaces are understood, but as soon as you go to minimal surfaces in R3 or S3, there's quite a lot that we still don't know. Okay? So let me recall some of what we do and don't know about minimal surfaces in S3. So as I said, it's a very classical topic, but for a long time, very little was known. So in particular, until the late 1960s, there were only two examples of closed minimal surfaces in the S3. So the first is the most obvious, the totally geodesic two spheres, the equators. And then there's the minimal embedding of the flat square torus in S3, the so-called Clifford torus. Okay? And one thing that's remarkable and maybe misleading about these examples is they turn out to be sort of extremely rigid with respect to their genus. So already in the 60s, Almgren observed that the equator, these totally geodesic guys, are the only minimal two spheres in S3. And that's true even if you're looking a priori at immersed minimal two spheres. All right, and then more recently, in Brendel's confirmation of Lawson's conjecture a little over a decade ago, we learned that the Clifford torus, this guy here, is the only embedded minimal torus in the three sphere. Of course, there are other ones if you go to the immersed setting. So if you're interested in the category of embedded minimal surfaces, closed minimal surfaces in S3, in genus 0 and genus 1, this is the ballgame. All right? And again, until the 60s, these are the only one known. You can ask what happens when we go to the higher genus setting. Okay? So in the late 60s and 1970, Lawson was able to construct embedded minimal surfaces of every genus and in fact at least 2 if that genus is composite. So he's doing this by using, say, the action of a product of dihedral groups on S3 in a natural way to tessellate your S3 and solve a plateau problem for a disk on the fundamental domains and using just the symmetries to generate these surfaces. All right, so using similar techniques, Karpukhin and Stirling constructed a finite list of new examples with these genera. So we know, for instance, already from this list that at least in genus 3 you have non-uniqueness, so you shouldn't expect a genus 3 Lawson conjecture. Okay, and then this technique was developed further by Choi and Saray more recently. And then there's sort of a program that started by Kapuleus and carried out more by his students Peter McGrath, Dave Weigel, and Yang, where they're using now implicit function theorem type techniques to start out with some singular minimal object, like an equator with multiplicity 2, or say 2 minimal surfaces meeting orthogonally, and they say, all right, well, in principle, these can arise as limits of smooth minimal surfaces. So for instance, if you have a minimal surface with multiplicity 2, you can imagine having 2 sort of sheets of minimal graph over it connected by little catenoidal necks. And in fact, by sort of very delicate implicit function theorem techniques, they're able to construct such a proximity in a lot of cases. Not every case you would like to, but so this gives rise to a lot of families with very large genus, because you only get this sort of approximation as the topology gets very large, and some prescribed asymptotic behavior, like certain symmetries. All right. Finally, of course, these things are critical points of the area functional. So you expect to produce them by doing Morse theory for the area functional, as we heard in Shin's talk. And whereas for an arbitrary metric, your Morse theory, you can only sort of work with the topology of the space of cycles, because we have a rich symmetry group here, you can also work with cycles that are preserved by different group actions. Okay, and so this was sort of pioneered by, sketched by Pitts and Rubinstein in the 80s, and fleshed out in more detail by Dan Kedover maybe 7 or 8 years ago. All right, and here at BIMS, we also have several experts on integrable systems methods. So I'll refer you to our chair for more details on this approach. All right, so I want to talk, so let me just remind you of some of the big open questions here. And I don't claim that these are necessarily the most fundamental ones, but there's some guideposts for seeing how much we understand about this space of minimal surfaces in S3. All right, so first we can ask a very cheap counting question, which is what are the number, n of gamma, of embedded minimal surfaces of genus gamma in S3, right? So we saw that for genus 0 or 1, it's just 1. For genus 2 even, I think it's the uniqueness of the genus 2 Lawson is open. But in fact, the situation's even worse. So we don't even know, for instance, whether this number is finite. So we know from work of Choi and Shin from the 80s that the space of minimal surfaces of fixed genus is smoothly compact. And so the only problem is you could have accumulation. So this is related to the problem of determining whether the area functional is sort of quote unquote more spot on S3. So are there any degenerate critical points modulo isometries? The guess is no, but this is a open problem. All right, on the other direction, we can ask about lower bounds. Can we at least say that we have lots as the genus gets large? And until recently, this was not entirely known either. So until about 1.5 years ago, it wasn't known whether this number even goes to infinity as the genus gets large. And this was confirmed by Kedover in late 2022, where he shows, okay, so you get this sort of slightly sublinear bound. And what he's doing is he's using min-max methods to produce some nice genus 2 surfaces in lens spaces, and then lifting these to produce high genus minimal surfaces in S3, which resemble doublings of the Clifford torus. So he's getting a lot of interesting new families that way, using sort of interesting geometric topology on the lens spaces. All right. So another cheap question we can ask, just to see how much we know, is what's the least area, let's say A of gamma, of a genus gamma minimal surface in S3? So, all right, one that's sort of easy once you have your hands on the basic tools of minimal surfaces is that the least possible area of any minimal surface in S3, realized in genus 0, is the equator. Okay, so you can see this, for instance, by taking cones over your surface to get a minimal object in Rn, and or R4 in this case, right? And the monotonicity formula tells you this is the lowest possible area you can have. All right. What takes a lot more work is getting information beyond this. And this was done by Marquez and Neves in the resolution of the Willmore conjecture. So as a corollary of their work, we know that as soon as the genus is at least 1, then you're bounded below by the area of the Clifford torus, which is 2 pi squared. So of course that took a lot of work to get that bound. And for genus 2 and higher, this is widely open, although there are conjectures they'll mention in a minute. So here's a conjecture, which I think was stated first by Rob Kusner in the late 80s. So he conjectured that in fact, not only is the least area minimal surface of genus gamma realized by this Lawson surface psi gamma 1, whose area is, we actually know, to pretty high order now thanks to work of Heller, and Frazé. He actually conjectures something much stronger, which is that these Lawson surfaces are Willmore energy minimizers in S3. So there's a statement not just about minimal surfaces, but in fact about the natural bending energy of any surface in S3, or in a conformally equivalent sense in R3 of prescribed genus. Okay? So our evidence for this is pretty weak at the moment. So for instance, the best that we know, well, so obviously this will be an upper bound on the least area, since it's coming from an example. And we know from Kuvertly and Schätzle that to leading order, as the genus goes to infinity, this is correct. So we know that you can't have a sequence of minimal surfaces with genus gamma going to infinity whose limiting area is less than 8 pi. Okay? And all right, so naively, if you're hoping to classify least area minimal surfaces, maybe you could ask that the space of minimal surfaces with fixed genus and small area below this threshold, is not too terribly large. Already, if you know a little bit about Cabuleus's work, you know it shouldn't be too small either. And in fact, as one corollary of the machinery I'm going to tell you about today, we know that in fact that the number grows at least linearly with the genus, even below this low area threshold. So in fact, there exist at least, let's say roughly genus over 4 non-isometric embedded minimal surfaces with area less than 8 pi. So already in sort of the lowest possible area where you can realize all topologies, you're getting piles of minimal surfaces as the genus gets large, at least linear with the genus. I should mention that I underline this at least here because I don't expect this to be even qualitatively sharp. Probably this should be much more than linear in general. All right. Okay. More, on the other hand, in these cases, we can actually check that at least as the genus gets large, these do all have area beating that of the Lawson surfaces. So maybe, unfortunately, we don't get any counterexamples to this fun conjecture of Rob with all these examples. Okay, so by construction, they also satisfy the conclusions of another major open problem for minimal surfaces in S3. To be clear, we don't make any progress in solving this problem, which is one that I think anyone who works on minimal surfaces has played with from time to time, which is this old conjecture of Yau's that says that for every closed embedded minimal surface in S3, well, we know just by the minimal surface equation that the 4 coordinate functions are automatically eigenvalues of the eigenfunctions of the Laplacian with eigenvalue 2. Okay, that falls out of what the minimal surface equation tells you in the S3 case. All right, but Yau conjectures that in fact these are not just eigenfunctions but first eigenfunctions. So 2 is the smallest eigenvalue. And in many, many cases this has been confirmed. So why is this interesting? Well, for instance, combined with work of Montiel and Ross, this could give you a new proof of the Lawson conjecture. It would tell you by work of Li and Yau that any embedded minimal surface automatically minimizes Willmore energy among surfaces of the same conformal type. But another reason this is interesting is that for reasons I'll tell you about in a moment, this would imply that embedded minimal surfaces in S3 are all critical points for an intrinsic variational problem for the first eigenvalue of the Laplacian. So we know that by definition, they're critical points for the area function. But in fact, this tells you that they should all arise in principle from variational problems coming from spectral geometry just on the space of intrinsic metrics on surfaces. So now let's switch gears for a moment and put ourselves in the setting of Antoine Enro's talk from yesterday and discuss some of those variational problems for eigenvalues. I mean, this would already be good, but yeah, that's certainly in all the cases where it's known, that's also true, and I think that's also expected. Yeah, okay. For these examples, that will also be true. All right. Any other questions before I move on? All right. Okay, so let's go to the spectral setting. So on a closed Riemannian surface, let's consider the eigenvalues of the Laplacian, where in my convention, lambda 1 is the first non-zero eigenvalue. And I'm also using my positive Laplacian convention. Okay, so the fundamental, that's maybe a political statement, but I'll stand by it. Lambda 1, as we learned in Antoine Rowe's talk yesterday, is characterized variationally as the infimum of this Rayleigh quotient among functions of zero average, right? So in other words, lambda 1 is giving us the optimal constant in this Poincare inequality. Okay, so if our manifold had boundary, this would be the first Neumann eigenvalue. All right, so as we learned from Rowe's talk yesterday, for those of you who were there, on a closed surface, this lambda 1 or any eigenvalue scales like length to the -2, so we can multiply it by the area to get a nice scale invariant quantity. And so of course there's lots of results going back to the 20s and 30s even for domains and Euclidean spaces saying that we can maximize or minimize certain eigenvalues of Laplacian under volume constraints to get canonical shapes. But there was a new direction opened by Hirsch in 1970 via a very simple observation, which tells us that in fact we can also solve some of these problems for intrinsic geometry. So not just for domains in some fixed ambient space, but for arbitrary metrics on a surface of given topology. So he shows in particular that for any metric on the two-sphere, the round metric always maximizes the first eigenvalue of the Laplacian. So this area normalized one. So the maximum possible is 8 pi, and it's realized if and only if your metric is round. Okay? So the proof idea is very simple. So I'll show it to you in case you haven't seen it before. So by uniformization, we know that we can always find a conformal diffeomorphism from whatever metric we're starting with to the standard two-sphere inside of R3. And moreover, because the space of conformal automorphisms of our two-sphere is very large, in particular we have this 3-parameter family of non-trivial ones coming from conformal dilations, you can actually arrange that that conformal diffeomorphism is balanced in the sense that each of the 3 coordinate functions has 0 average on n. So in particular, those coordinate functions become test functions for this Rayleigh quotient definition of the first eigenvalue. And plugging that in, we see that, well, that means the energy is bounded below by lambda 1 times the L2. And then we just read this through. Well, because phi is conformal, we know that this energy here is exactly twice the area. And then that's bounded below by the first eigenvalue times, well, we sum over the squares of these phi i's. It's taking values in the two-sphere, though. So the sum of those squares is 1. And so we see this is bounded below by lambda 1 bar. And then finally, if equality holds, then we know that we can read off this conformal map is also a map by first eigenfunctions, and it's easy to conclude. Okay, so that's this classic observation of Hirsch from 1970. And it opened up the sort of beautiful story that was picked up later by Berger. So Berger then begins to ask about what happens if we maximize this lambda 1 bar over other topologies or other conformal types if we want to restrict ourselves a little bit. And so, for instance, by playing around with metrics in the torus, he formulated this conjecture that among all metrics on the torus, the maximizer for this lambda 1 bar should be the equilateral torus. Okay? Which is easy to, maybe not easy, but an exercise to see that at least among flat torids, it's the maximizer. All right. So later, Yang and Yao, and there's some improvements later by El-Soufi and Elias, they showed that at least there is a nice upper bound for any genus. And the idea is to take Hirsch's idea, and instead of applying it with a conformal map, which is no longer available in this case, we can apply it to some branched holomorphic cover. And essentially the same idea is that you get a corresponding bound, but now with the degree of that map multiplying the 8 pi. And so by optimizing on the degree of that map, you get a bound like this. So you have some universal upper bound for any metric on the surface of genus gamma, which grows linearly in the genus. And while this bound isn't sharp in general, the linearity in the genus is. Okay, you can get linear lower bounds via hyperbolic metrics. Okay. So in 82, Li and Yao improved on this a little further. So they sort of stretched the Hirsch trick almost as far as it could go by introducing something called a conformal volume, which involves conformal maps into higher dimensional spheres. And in particular, using this, they're able to get a good trick for computing conformal volume, for computing these first eigenvalues for lots of conformal classes, not necessarily maximizers in among all topological types. And so, for instance, for RP2, where there's only one conformal type, they were able to show that the maximizer is the round metric. Okay. Let's see. And moreover, they start to make the connection here that there's some relationship between these eigenvalue optimization problems and minimal surfaces in the sphere. But this wasn't really fully understood or exploited until this breakthrough of Nadarashvili's in the 90s, which settled Berger's conjecture. So in the mid-90s, Nadarashvili proves Berger's conjecture, and unlike all the previous cases where these lambda 1 bar maxima were computed, instead of comparison with some other external quantity, he's just doing this via direct attack. So he argues that a maximizing metric exists, and then characterizes by sort of looking at the quote-unquote Euler-Lagrange equations. That's not entirely the right way to call it in this context. You're able to classify. So let me say a little bit about that. So first of all, what would the Euler-Lagrange equations for this problem actually look like? So here's an exercise, not entirely trivial, but not too hard either. So suppose you have a unit area metric for which your first eigenvalue of the Laplacian is simple. So generically, we know this is proved by work of Uhlenbeck. Well, then this eigenvalue functional is going to be differentiable G. And moreover, if you differentiate in the direction of some symmetric 2 tensor H, it's given by the pairing of H with this tensor, which looks like, okay, so you have this sort of trace-free piece that looks like a stress energy tensor for your eigenfunction, and then you have this pure trace piece that's 1 minus your eigenfunction squared. Okay? So suppose we had now a metric like this, which was in fact a maximum, right? So if this lambda 1 bar were maximized by a metric with simple first eigenvalue, well then that would tell us that this 2 tensor has to vanish, right? For this L2 normalized first eigenfunction. Okay, but let's do the simplest thing. Even if we only knew that this were true, that this were maximizing in a conformal class, but we could still know that this pairing with the metric G would have to vanish identically. So even if we only knew that, well, we could pair this with the metric G, and this would tell us exactly that lambda 1 times 1 minus phi squared vanishes identically. So in other words, if we're a conformally maximizing metric with simple first eigenvalue, well, then the square of that eigenfunction has to be constant. But clearly this is absurd, right? Because this phi is a non-constant, smooth function, so its square can't be constant, right? Okay, so we can't in fact have a maximizer with multiplicity 1 for the first eigenvalue, and in particular this tells us that any reasonable notion of critical point for these eigenvalue functionals will have to be a non-smooth critical point. So in general, these are only Lipschitz. All right. On the other hand, once we learn to interpret critical point correctly, something much more interesting happens, which is that if we're critical, then we know we have some multiplicity for the first eigenvalue. And in fact, there does exist a collection of first eigenfunctions as opposed to a single one, such that the sum of their squares is constant. So for instance, by scaling, the sum of squares is 1. Okay? And moreover, looking at the second part of that tensor, if G is lambda 1 bar critical among all metrics, then we know that in fact this sum on d phi tensor d phi is exactly this sort of energy of this map times the metric. Right? So let's read that off a little more geometrically. So in other words, if G is only conformally critical for this lambda 1 bar, then there exists a sphere-valued map to some n-dimensional sphere where you can bound that n by the topology by work of Chung. You can find a sphere-valued map to eigenfunctions. And if in fact we're critical not just in a conformal class but among all metrics, then that map has to also be a homothety. Read that off here. Okay? All right. So let's parse that out a little more geometrically still. So it's a very easy exercise to see that a sphere-valued map by first eigenfunctions like this must be harmonic. So in other words, it's a critical point for the Dirichlet energy among sphere-valued maps. So already this is, very bizarre, right? That when you're looking at critical points for this intrinsic variational problem on the space of metrics, the output gives you the solution of some extrinsic variational problem on the space of maps to a sphere. It's very, I think, non-intuitive the first time you see it. And another important fact, going back to work of Uhlenbeck, is that if you have a harmonic map from a surface which is also conformal, then the image of that map is exactly a minimal surface, possibly with branch points and self-intersections in the n-sphere. Okay? So in particular, if we have a lambda 1 bar critical metric, then it has to be induced by a minimal immersion by first eigenfunctions. Okay, so this was Nadarashvili's insight. And then in the case of the torus, we're in good shape because in the case of the torus, Montiel and Ross showed in the 80s that the only such metrics, the only such minimal emergence by first eigenfunctions are inducing the flat metric. And in particular, there are only two options, the Clifford torus, square guy in S3, or there's the so-called Bryant-Ito-Montiel-Ross minimal embedding of the equilateral torus in S5. And then by direct comparison, we see that the equilateral torus wins for this maximization problem. So that's Nadarashvili's resolution of this Berger's conjecture. All right. Questions before I move on? All right. So what about other topological types? Well, since the 90s, we only know a couple more examples for these lambda 1 bar maximizing metrics. So building on the same kind of techniques as used in Nadarashvili's proof, others work of Jacobson, Nadarashvili, Polterovich, and later El-Sufi, Giacomini, Jazar, which tells that the Klein bottle, this lambda 1 bar is maximized by a non-flat warped product metric induced by an explicit minimal embedding in S4. Okay, I emphasize this non-flat here just to show that from all the examples we've seen so far, you could imagine that these are always going to be constant curvature. So this is not the case. You're getting more interesting objects in general. Okay. And more recently, in the case of genus 2, Nayatani and Shoda were able to show that somewhat bizarrely, because this doesn't happen for higher genera, equality actually holds in the Yang-Yao inequality. So this lambda 1 bar is actually maximized by a metric induced by some branched holomorphic cover of the 2-sphere from, say, the Bolza surface on the genus 2 guy. Okay, so in particular, in this case, note that the maximizing metric has some conical singularities, right? Coming from branched points, say, of this map. Okay. Oh, actually pinning down precisely the maximizing metrics is a hard problem. Can we at least say that they exist, and then later on, as our classification results for minimal emergence by first eigenfunctions improve, maybe we can try to say things more explicitly. So what about existence? Well, the conformal story is thankfully well understood in the last decade. So there are now several different proofs, but the first major one was by Petrides. So he showed that for any conformal structure on a closed surface, there is going to be a lambda 1 bar maximizing metric in that conformal class. And the story here formally ends up looking a lot like the resolution of the Yamabe conjecture, where it comes down to ruling out some numerical inequality, to proving some numerical inequality, showing you can't degenerate and bubble off to the round 2 sphere, and Petrides confirms that inequality. Yeah. All right, so in particular, once you do it for a conformal structure, well, we're in dimension 2, so our moduli space of conformal structures is fortunately finite dimensional. So in principle, this reduces the existence problem to a finite dimensional optimization problem. But, of course, this moduli space is also non-compact, and so a priori, you could have a maximizing sequence of conformal classes escaping to the boundary, right? If you're maximizing sequence, you have some next pinching off. Okay, so the goal is to rule that out. And Petrides, again, was at least able to reduce this to a very explicit numerical criterion. So he says that as long as this maximum value, the soup on the surface of genus gamma, is strictly larger than the soup on the surface of genus gamma minus 1, the non-strict inequality is easy to show, then a maximizing metric exists on the closed surface, I should say, of genus gamma. Right? So as long as you have this numerical inequality, that's enough to rule out degeneration to the boundary of your moduli space. Okay. So this seems in principle like it should be easy, right? You know existence for one genus, so all you have to do is construct some other metric on the higher genus guy to show that it beats it, and you're done, you have your existence. But actually showing it simultaneously for all genera turns out to be very hard and is still open. Although in a moment I'll show you a reduction, which seems like it gets us very close to showing it. Okay. All right. So how could you actually try to show this simultaneously for all genera in practice? So the first strategy is basically what I described, right? So let's go by induction. And okay, so we know that existence works up to some genus gamma, and then let's assume, to get a contradiction, say, that this inequality breaks down from genus gamma to genus gamma plus 1. Okay. So then let's look at the maximizing metric on the last surface where we know it exists, and let's just try to perturb it, for instance, to get a nice maximizing metric on the higher genus guy by adding a handle in some very clever way, right? So what are the past attempts to prove the strict inequality? Well, the idea, maybe I'll start drawing a picture here. Right, so you start from your genus gamma surface. You cut out maybe some tiny disks, and then you glue on a handle, just topologically for now, right? And the idea that people have tried is to choose a metric on that handle in some very, very clever way, maybe to mimic some sort of hyperbolic cusp, right? To just explicitly produce something, and usually an L infinity metric, but I claim that for the purpose of these inequalities, the regularity doesn't matter so much. So to produce some metric where you can show explicitly, by doing a very careful asymptotic analysis in the limit as this thing shrinks, that in fact your lambda 1 bar of that metric beats it. Okay? But in principle, if you're hoping to do this, this means you have to choose your metric extremely carefully, and it turns out people have not been able to actually carry this out so far. I mean, you can see preprints on arXiv claiming this, but unfortunately there are gaps. Okay? All right. So let's try a strategy which is in principle a little simpler, because it reduces this infinite dimensional problem of choosing one particular special metric to a finite dimensional one that seems a little more tractable. Okay, so let's start from the same place. So let's suppose we're at the first genus where this breaks down, and let's try to get a contradiction again. And let's again look at our maximizing metric on the lower genus surface. And now, instead of trying to produce a metric that violates the inequality, that violates this equality rather, this tells us that for every conformal class on this higher genus surface, we have this inequality. So the conformal supremum of the first eigenvalue is bounded above by this lambda 1 bar. Okay, and remember that we know the existence of conformally maximizing metrics, and they're realized by harmonic maps. So in fact, this is giving us some energy bound on some harmonic map. Okay? All right. So instead of choosing this distinguished metric, let's instead try to sort of just cheaply choose a distinguished conformal class and get a contradiction. Okay. And so again, our starting point will be the same. We fix some points. It's important for what I'm doing here that we fix them in an arbitrary way. Let's cut out some disks, say of radius epsilon here, or just size epsilon. I won't be too precise. So we have some disks here of size epsilon. And let's just attach a flat cylinder. Right, so this will be, say, a circle at scale epsilon across this interval of length L epsilons. Note this, for the conformal purposes, this epsilon is kind of fake, and the only parameter here is this L. Except the epsilon is not fake on the sort of the level of the base manifold here. Okay, so now we're just using this to get some conformal class on the higher genus surface. All right, so the cartoon idea of the argument I want to show you is the following, and this is sort of what we had in mind when we first were developing this, is okay, we know from the existence theory for these conformal maximizers that there's going to be some harmonic map by first eigenfunctions on that modified surface whose energy is going to be bounded above by this lambda 1 bar on the lower genus surface. Okay? And the idea is that that should in fact be very close to a map by first eigenfunctions down here, and that should tell us that all of the energy should be stored down here, so we have very little energy in the handle. Okay? And in fact, if we replace this harmonic map with the following, so instead of working with this actual harmonic guy, all we need to do, using previous work of myself and Misha Karpukhin, is we find some f epsilon from this modified guy into Sn, such that this energy bound holds. So it's bounded above by this lambda 1 bar on the lower genus surface. And the catch is we ask that it be balanced on, say, this lower genus guy with the holes cut out. So we ask that when we remove those epsilon disks around P and Q, we satisfy a balancing condition here. which makes us our coordinates good test functions for the Neumann problem on this base guy with the holes removed. And another nice exercise for you is that first Neumann eigenvalue, when you remove those disks, is going to be bounded below like lambda 1 of the whole surface up to something of order epsilon squared. Okay? So using that, and essentially applying a version of Hirsch's trick, you get the following. And note that the following doesn't require any sort of serious PDE argument. It's all soft things at the level of W12. Okay? So if we restrict this F epsilon to the surface with the disks cut out, in fact, we can argue it's going to be epsilon close in W12, maybe when we harmonically extend inside those disks, to a map by first eigenfunctions on the lower genus surface. Right? The projection to the first eigenspace is almost all of it. Okay. Moreover, well, we know that if it's close to a map by first eigenfunctions, then most of the energy is going to be in here, and all that's left here is what's left over, so we have epsilon squared of energy inside that cylinder. And the next step is the really deep one. We have to use a deep theorem in analysis, the fundamental theorem of calculus, to tell us that with that energy bound, we know that if we look at the averages of this map on these little circles here, then in fact they have to be very close together. Okay? All right. So in particular, where do we end up? Putting all this together, we see by taking just projection to the first space that we have some map by first eigenfunctions, which is almost sphere valued in a W12 sense as epsilon gets small. And if we just fix some L bigger than 1, say, we can actually check that since we're in the first eigenspace and all norms control all other norms, then that closeness at the level of averages is going to tell us that pointwise phi epsilon of p minus phi epsilon of q, that difference looks like this. You get something, you can ignore the L dependence because we're going to fix that, something like epsilon root log epsilon. Okay, where the log there is just the price you pay for W12 not quite embedding into C0 in dimension 2. Okay, and so if we just take epsilon going to 0, what have we actually ended up with here? Well, we see that if this inequality fails, then for every pair of points in our lower genus surface, because remember I chose an arbitrary pair of points to start, there exists some sphere-valued map by first eigenfunctions identifying those 2 points. Okay, so let's think about that. Let's go to S2 first. We already know that the strict inequality wants true in that case, but let's go to S2. For S2, the only sphere-valued maps by first eigenfunctions are exactly the totally geodesic embeddings. So in particular, not only will we not find maps identifying every pair of points, but we can't find maps identifying any pair of points, right? You only have embeddings. Okay, so you can't identify distinct points. All right, if we go to, say, the equilateral torus, pretend we don't know the inequality at that stage, well, it gets a little more interesting here, and I think this is sort of probably the worst case, because now, in addition to, say, the minimal embedding into S5, we also have, for your sort of 3 smallest lattice directions, for each of these you also get an S1 valued map by first eigenfunctions. And of course, for each such of these maps, you'll get some foliation such that any 2 points in a given leaf will be identified by this map. And but of course, if you go to any direction apart from those lattice directions, any pair of points will violate this conclusion. And in fact, it seems this should never hold. So we conjecture that for every lambda 1 bar extremal surface, so a minimal surface by first eigenfunctions in the sphere, there will exist some pair of points which are not identified by any eigenmap. Okay? And if that's true, then it follows from this machine that this strict inequality always holds, and therefore the existence theory always goes through. Okay? So let me share a little evidence in favor of this. So first I'll note that if you had a counterexample, well, you could also take pairs of points where as you take them getting closer and closer together, you also end up with an eigenmap that annihilates, whose differential annihilates any prescribed vector in the tangent space. And by playing around with the Bachner identity, you can see that this would force your surface to have negative curvature. And it's actually an open problem whether, in fact, a minimal surface of negative curvature can exist in the n-dimensional spheres raised by Yau in the 80s. As we'll hear later in Antoine's talk, you can find some that get very, very close to negatively curved, even with constant curvature in an integral sense. But so a counterexample would be interesting for this reason. Some reason to believe it's true, though, is that if we take the same statement and replace 2 points with 3, okay, so we ask that we want to say that, there's always going to be some triple of points that can't be identified by any eigenmap. Well, that turns out to be true. Okay, and the idea is now, just as the 2.1 told us that we could have df annihilate a prescribed tangent vector, this would tell us that we could have df annihilate the whole tangent space, right? So we could find an eigenmap where df vanishes at a prescribed point. On the other hand, for such a map, it's in standard computation to see that df squared is identically 2 away from some finite list of conical singularities. So that can't happen. And as a corollary, by sort of taking the same handle attaching argument, but with sort of a tripod in place of the handle, we see that we always have strict inequality from genus gamma to genus gamma plus 2. So we get sort of a half-existent statement for arbitrary genus where a maximizer exists for every other topological type, which is kind of bizarre. But I would expect that this holds for every genus. When we first got here, we thought we would prove it in a week, but we haven't yet, so you can take a stab at it. All right, but all of this is fun. This is a very classical optimization problem. It wasn't really what we were trying to do here, so let me tell you what we're really trying to do. Okay, so now let's take a closed surface, and let's repeat the same things, but add some symmetry. And we're not just going to do this in an arbitrary way, but let's start out arbitrarily for now. So let's take some nice discrete group sitting inside of the diffeomorphism group of our surface, and we can play the same game. So we can look at metrics that are invariant under the action of that group, and then just look at the supremum of this lambda 1 bar over such metrics. Okay? So I claim it's not hard to show once you know how to do it in the trivial case, to show that a metric realizing the supremum has to be induced by an equivariant branch minimal immersion into some n-sphere. Okay? All right. But for specific symmetry groups, you can say a lot more. So for instance, let's suppose we have a group which contains some Z2 component, which is a reflection exchanging two genus 0 components of n. Okay, so you can imagine we have two spheres, and then we attach them by some necks, and we do this in such a way that we have a reflection in the fixed point set cuts all those necks. Okay? So we're genus 0 on each fundamental domain. All right, so using a variant essentially of the Hirsch trick for the Neumann eigenvalue on the fundamental domain, we can see that lambda 1 bar in this case is strictly bounded above by 16 pi. Okay? And using a variant of some classic results of Chung that tell us that the multiplicity of the first eigenspace on a 2-sphere is always at most 3, we can see that in fact for a metric like this, this multiplicity is always at most 4. Somehow the Neumann part gives you 3 dimensions as in Chung's result, and you have an extra Dirichlet one corresponding to odd eigenfunctions under the reflection. Okay, so why is this nice? Well, that means if a metric realizing this exists, well then it's giving you a map into S3, right, because it's going to R4 at most. And moreover, it's going to have area less than 8 pi. And as a consequence of the monotonicity formula, results of Li-Yau, you know that if you have a branch minimal immersion with area strictly less than 8 pi, it always actually has to be embedded. So a priori, we're getting these branch minimal immersions to very high dimensional spheres. But if we impose this kind of symmetry, now we're in this very classical setting of looking at embedded minimal surfaces in S3, which is kind of the thing we were aiming at in the first place. Okay. All right, but of course the existence, as we already saw in the case of the trivial group, is not necessarily an easy thing. So as in the case of the trivial group, we can show that the conformal maximizing metric, I say here that it always exists. That's not quite right. There's some criterion, which is sort of easy to check in every application that we've looked at, would expect the maximizer always exists. All right, but then this reduces you to the problem of looking at degenerations in the boundary of this symmetric moduli space. Okay? And in this case, you get a criterion which looks a lot like the one Botrytis has in the case of the trivial group, which basically says you want to have strict inequality under sort of equivariant or invariant neck pinches. right? So when you get some, when you pinch off a neck in an invariant way, you want to show that you have strict inequality on those associated suprema. Okay. But fortunately, we can handle this via exactly this handle attaching trick I was just showing you. So, all right, so if this inequality fails, but the latter one is realized, then the same 2-point lemma, now it's a little more restricted because we can't quite choose those points in an arbitrary way. They have to respect the symmetry. But it tells us that for this lower genus guy that we degenerated to, we have a minimal surface in S3 for the reasons I just outlined, and it has to lie at the intersection of S3 with the quadratic cone. That's one way of interpreting this extra map by first eigenfunctions. Okay? And if we have a map, if we have such a minimal surface, which is the intersection of S3 with some quadratic cone, it's an exercise to see that it has to be the Clifford torus. Okay? So it's the Clifford torus. It has to have, then we know what this lambda 1 is exactly. It's 2 pi squared. Actually, no, there's an extra 2, so it should be 4 pi squared. All right, and then we can then argue using the genus 2 Lawson surface, which is known to be embedded by first eigenvalues, eigenfunctions, and satisfies any possible symmetry we can impose, that in fact we can always beat this bound at the genus 2 threshold and then at any higher threshold. So in fact, in all of these cases, we get the strict inequality with 2 pi squared, and that tells us by contradiction that we get the strict inequality in every case. Okay? So applying this, for instance, with the Z2 cross Z2 actions, where the first reflection satisfies this topological constraint, but the second reflection, now we can allow the topology of the fundamental domain to vary, right? We can see that, in fact, we have at least this linearly many, as advertised before, just by seeing that somehow there's, certain ones have to be topologically distinguished, right? Okay. And moreover, we aren't restricted to Z2 cross Z2. We can look at Z2 cross G actions, where G is any nice finite subgroup generated by reflections. Okay. So another corollary of this story. So if instead of asking about critical points for the area functional in S3, we asked about critical points for relative cycles in just a hemisphere, so cycles relative to boundary, then the critical points of those are called free boundary minimal surfaces. And under reflection, in this case, they're exactly the same as half of a reflection invariant minimal surface. So these results also tell us, for instance, that we have embedded free boundary minimal surfaces of any topology in the hemisphere S3+, which, as I'll mention in a moment, is related to some problems that have been open for a while in free boundary minimal surface world. Okay. Before I go to the boundary setting, any questions? Yes, that's in the last 2 slides. Okay, let's see if I get there. Okay, if not, I'll show them to you after. Okay. All right, so let's discuss this free boundary / Steklov story. So I'll start from the spectral side in this case. So if we have a surface with boundary, we can look at the spectrum. Well, there are lots of spectra we can look at, but the one that turns out to be most relevant here is that of this Dirichlet to Neumann map, where we take a function on the boundary, take its harmonic extension to the interior, and take the first normal derivative to get another function on the boundary back. And all right, so this turns out to be a nice operator. It has a discrete spectrum. You can once again interpret these via a Rayleigh quotient, where now instead of looking at, instead of your denominator being integrals with respect to the area in the interior, it's now integrals with respect to the length measure on the boundary. Okay. All right. And once again, there's a natural scale invariant normalization of these eigenvalues. This is a first order pseudo-differential operator, and we can multiply these eigenvalues by the length to get a nice scale invariant functional of the metric. All right. So already in the 50s, people had some optimization results for these. So Weinstock showed he was really working with planar domains, but it works for arbitrary metrics. That on the disk, the best you can do for this first eigenvalue is the standard metric on the unit disk, where it's 2 pi. But this story doesn't really enter into differential geometry world until work of Fraser and Shane about 15 years ago, where they realized that there's this beautiful parallel between the variational theory for these Steklov eigenvalue functionals on surfaces of boundary and the story that had been developed by Nadarashvili and others in the closed case for the Laplace eigenvalues. Okay, so if you're in a manifold with boundary, I'll just mention, I said this in words, but I'll put it on the slide. The free boundary minimal surface is exactly the condition you get when you look at critical points among relative 2 cycles. And what you get is a minimal surface whose boundary meets the boundary of omega orthogonally, right? That's kind of the homogeneous Neumann condition here. So if you like In the world of geodesics, this is like billiards in a planar domain, for instance. Okay. And one of the most natural settings, in some sense the simplest one, is the standard unit ball. This is somehow the analog of S3 in this world. And even though free-boundary minimal surfaces have been studied since the 40s, until recently there were only two examples known, the equatorial disks and this critical catenoid, so a natural free-boundary minimal annulus. Okay? So Fraser and Shane observed that analogous to Nadarashvili's work on the Laplace eigenvalues, if we have a critical metric for this first Steklov eigenvalue, it has to be given by a free boundary minimal immersion into some ball by first Steklov eigenfunctions. Okay? And building on this observation, they were able to classify the maximizer for the annulus and show it's exactly this critical catenoid. And moreover, they observed if you have extremal metrics on any genus 0 surface with any number of boundary components, they have to be embedded free boundary minimal surfaces in B3. Okay, so you get embeddedness and codimension 1 here, as in our setting. Okay, so the current status, the existence theory is very much analogous to where things are in the Laplacian case. So the conformal maximization is known by Fraser and Shane, and the problem is proving the strict inequality, ruling out degeneration to the boundary of this moduli space. Okay, and in particular, if we let sigma 1 of gamma k be the soup for genus gamma and k boundary components, we have the following result of the treatise, which says that as long as we can rule out two degenerations, we get strict inequality when we lose a boundary component, or when we lose genus and gain a boundary component. You can imagine we have a thin strip connecting two boundary components that pinches off. Then, in fact, we do have a maximizing metric. Okay? So by analogs of the handle attaching trick, that I won't get into in the interest of time, we can show the following. So in fact, we always get the strict inequality for losing a boundary component. That one's somehow easier. And then if we don't have our inequality in the genus drop case, then at least we can show that for any pair of points in distinct boundary components, we have some eigenmap identifying. Okay? And so this turns out to suffice. So again, we conjecture that the latter is impossible, right? So we should just be able to finish the existence theory, and it reduces this to this very concrete problem about whether you can have free boundary minimal surfaces whose boundaries lie in the intersection somehow of a huge pile of quadratic cones. Okay. All right. So as a corollary, we're able to show that on a compact oriented surface with genus 0 or 1, and any number of boundary components, a maximizing metric always exists. So in the genus 0 case, it's enough to show the loss of boundary component, right, which we said we always have. In the genus 1 case, maybe I won't say too much in the interest of time, but the point is you reduce it to showing that this point identification problem can't hold on the critical catenoid. And you can check that this fails in the critical catenoid just by taking antipodal points. Okay, maybe I'll skip over that. All right. On the other hand, all right, if we look at our genus 0 maximizers, these are going to be embedded free boundary minimal surfaces in the 3-ball. The genus 1 ones are going to be in B6. And in general, as the genus gets large, these are going to be very, very high codimension. So we're interested in finding examples where, as in the S3 case, we're forcing things to be codimension 1 and embedded. Okay. And in particular, in light of Fraser and Shane's work, the study of embedded free boundary minimal surfaces in B3 has really taken off in the last decade. And so, for instance, people have used variants of the Capuleus techniques, these double union desingularization constructions, and various min-max methods to produce lots and lots of examples. But one of the sort of central questions people have been after that's been hard to pin down with either of these techniques is whether you can do any prescribed oriented topological type. So an analog of what Lawson first showed in S3, that you can realize any genus by an embedded minimal surface. Okay, so with the doubling techniques, it's very easy to prescribe behavior, but only as the topology gets very, very large. With the min-max methods, it's very hard to control topology, especially from below. There's sort of good techniques now for controlling topology from above, but showing that you don't lose topology is very hard in that case. Okay, so with these techniques, by this symmetric maximization, which I'll skip over the details, again, we need to impose a reflection which cuts now all next and also all boundary components. Then we show that if a sigma 1 bar maximizer exists in the symmetric class, it's given by an embedded free boundary minimal surface with area less than that of the double disk, which turns out to be enough to guarantee embeddedness. All right. And so for many of this type, we can carry out the maximization problem completely. And even just for a single Z2, this allows us to solve the topological realization problem. So there exist embedded free boundary minimal surface in the ball of any topological type, orientable, and moreover area less than 2 pi. Okay? So Mario Schultz, a postdoc at Münster, does a lot of interesting numerical work with free boundary minimal surfaces. And he'd actually conjectured independently you should have a family like this around the same time we were writing up our paper. And one of the nice consequences of this is that Mario generates lots and lots of images numerically. So we have some pictures of what these should look like. Okay? So you'll see that these are sort of converging, it looks like, to a double of the disk. And moreover, you have this interesting phenomenon of genus, as it gets large, sort of moving out to the boundary. And you can actually see, sort of when you get your hands into the variational theory, why that should be the case, that genus is moving out to the boundary as it gets large. Okay. All right, so I'll just be brief about this. So by taking Z2 cross Z2 actions, where we vary topology in a suitable way, we can see that for any prescribed topology, the number of these surfaces actually grows at least linearly in the genus again. In fact, you once again get sort of genus over 4 growth. Again, I wouldn't expect this to be sharp. And in genus 0, without imposing this reflection symmetry, what Fraser and Shane already give us embeddedness. And in this case, we can show that in genus 0, for any number of boundary components, we also get the sort of linear growth in a number of boundary components for the space of genus 0 free boundary guys, even just with Z2 cross Z2 symmetry. Okay, so maybe what I'll do now is skip over these last slides and someone can ask me about them in the question section. All right, thank you.
Now, many thanks. Are there any questions?
Yep.
So you're in your 2-point lemma.
Yeah.
What happens when P converges to Q? When you take P converting to Q, I don't have a very clear picture of the corresponding emergence.
So I said this, but probably too quickly, which is that, okay, so a picture of the emergence, I don't know, because they shouldn't exist, right? And they shouldn't be emergent, right? These are now just maps, so they could be like S1 valued maps, for instance. But the thing that you can say is that in the fixing P and letting Q converge to P, then we get some first value, map by first eigenfunctions where df annihilates that tangent vector. And that's, for instance, how you get this negatively curved thing. As far as what those maps look like, they shouldn't exist. But
Okay, so second question.
Yeah.
Do you have an intuitive explanation of the behavior of the holes in the picture in the free boundary case? So why do we have to escape to the boundary?
Oh, sure. So remember, we're trying to maximize this first Steklov eigenvalue. And that first Steklov eigenvalue is, it's the infimum of this Rayleigh quotient, where this is now on the boundary, right? So this is boundary of M for ones with average 0. Okay, so now let's suppose we're trying to get lower bounds, for instance. So we're trying to maximize by hand. Then we know that, okay, so if we have, say, an odd eigenfunction, so we're cutting our thing in half, so we're just getting a disk with some sort of holes and marked boundary components, say. So you've cut off your fixed point set, or cut off a fundamental domain, and these are what you're seeing of the boundary components, and these are the things corresponding to the next. Okay? So if you have, say, an odd eigenfunction, so you're trying to bound this on the odd part, well, you know it's going to vanish here. And you want to say that somehow by vanishing here, the energy controls what's happening on the boundary very well. And so the best way to do that is to put these as close as possible to the boundary. That's kind of the rough idea.
Any further questions?
Is there anything that
Yeah, no, so unfortunately there are very few results along the lines that if you have a minimal surface in S3 with these symmetries, say, then it has to be this one, right? So there are cases where I know it's the equator whenever it's a two-sphere, and whenever it's a torus, I know it's the Clifford torus. And let's see, there are certain cases where, okay, if you sort of impose as much symmetry as possible, then there are cases where we can say by work of Capoulias and Weigel, it has to be the loss of surfaces. But in general, it's very hard to pin down because there are just very few classification results.
What was on your last slides?
Thank you, yeah. Okay, so I'll still be brief because I don't want to keep people from lunch. But basically, the point is that we can actually say sort of, we get more precise information here beyond the topological control than you typically get from, say, doing variational methods for the area. So you get nice lower bounds, again, by sort of constructing test metrics by hand. And so, for instance, for all those genus gamma guys, we can say for this, we have this family that grows linear with the genus. We can actually always show if the genus is large enough, they're bounded below by area of the Lawson surfaces. And moreover, as soon as you're sort of not in the Lawson case, you go from this 8 pi minus constant over genus behavior to something like 8 pi minus e to the minus square root genus. And in fact, most of them are in this range of converging very, very rapidly exponentially to 8 pi. Okay, and in fact, in all the non-Lawson cases, we can also show that instead of going to a union of orthogonal two spheres, which is what happens for the Lawsons, the only thing that can happen within this family is that you go to a double equator, which is conjectured to be the case, without any of these assumptions. And then some analogous results in the free boundary case, and some conjectures about a family we construct, which sort of should be thought of as the free boundary analog of the Lawson surfaces. I don't want to keep people from lunch.